We'll be talking about 1.7 bifurcation. So we have done if you have done your project, you will see a problem recently. And what you have is a logistic growth combined with a harvest of fish. Okay, so let's see what it means. You have y prime equals 0.3, 1 minus y over, for example, 2000 or something like that. Okay, actually, let's use the real number. Our n is going to be 2000 and 0.3, 2000. Yep, that's right. Now what we have is our logistic growth, but after that we actually added one more term, that is minus h and times y. So we say, well, the first part is going to be the logistic growth. If you leave the fish to be, eventually it's going to be growing towards 2000, which is the maximum capacity of your lake. Now what we want to do is we want to harvest the fish with a certain percentage rate, with a rate h. Okay, so as we start harvesting the fish, certainly that will affect the dynamics, the solutions of your differential equation, because basically you are changing the differential equation. Okay, and then we try to model it using Euler's method, a numerical method in Python. So what we have is something like this. From here, we can see if we harvest at the rate of 0.15, basically the whole thing just cancels itself. The thing stopped growing and stopped reducing either. So it's almost like the fish you're fishing is exactly the same as the fish they're producing. Therefore, you achieve a constant growth rate 0. You don't change at all. All right. Now, if you fish a little bit lower than that, you can see if you don't fish at all, you have a logistic growth. But if you start fishing, you can see, well, you still have the growth. It just changed the final population because you're fishing now, right? So that thing should reduce a little bit. It cannot hit 2000 anymore. So you keep doing that. Basically, what you do is, if you change h for a small amount, your final stable population will reduce for a fixed amount, which is fine. Until you hit 15, you achieve the balance. The thing doesn't grow. They balance themselves. But if you just hit a little bit more than that, you can see what's going to happen. Okay, let's wait a little bit. This is a little bit slow. Okay, so this is what happens at 15. But if you fish lower than that, more than that, you can see the whole thing actually fundamentally changed the behavior. That is, you went from growing to a maximum capacity, okay, to reducing, and eventually if you fish too much, you can see this one actually eventually just dies out. Okay, from here you can see, well, when you try to change the parameters in the differential equation, in our case, which is the harvesting, your solution will change. So, change of parameters in the ODE will lead to the change of solution. In general, it's no big deal. You change your, for example, growth rate a little bit, then your solution changes a little bit. It still has a horizontal asymptote. It's just a different value. Okay, but at some point, at a very critical point, or let's say a critical point of the parameter, then a small change can actually lead to a dramatic change. A small change in parameter. Usually a small change of parameter should lead to a small change in the solution. But at a critical parameter, a small change in parameter will change the solution dramatically. So let's still do things in this way. So let me organize a little bit. This is not part of it. At the critical parameter, okay, a small change erase this, and then at some critical parameters, okay, a small change in parameter can lead to a dramatic change in the solution. Usually a small change only give you a small change in the solution, but it can give you a dramatic change in solution. What do you mean by dramatic change? That can be before you have some stable growth, sustainable model, but after you change the parameter for a little bit, after you hit the critical point, what's going to happen is the whole thing actually goes to extinction. Okay? It went from increasing to decreasing. You can have all those kind of dramatic changes. So it's not just increasing to a different amount. You actually fundamentally change the dynamic of the differential equation. Okay? And usually how we quantify it, we have two things. For our concern, number one, it changes the number of equilibriums. Okay, for example, before we have 3 equilibriums, but if you just keep tweaking your parameter, at some point, your 3 equilibriums become 2 equilibriums. 1 equilibrium is just gone. Okay. Second, you will change the type of equilibriums. For example, equilibriums. Okay. For example, you hit a certain point, and suddenly the sink become a source, or the source become a node. So that means we dramatically change the behavior, the long-term behavior of the solution, okay, which is quantified by the equilibriums. In this situation, we say a bifurcation happened. Okay, so that's what we want to learn now. So let's wrap things up again. We now have some parameters in the differential equation, and as the parameter change, the behavior of the solution is going to change. Usually, a small change will only lead to a small change in the solution, but at some special values of the parameters, if you change the parameter a little bit, your solution will fundamentally have a dramatical change. And to quantify that, we basically say a fundamental change usually we refer to the change of number of equilibriums or the change of type of equilibriums. In this case, we call a bifurcation occurred. And what we want is, given any kind of differential equation with a parameter, okay, how do we know where the bifurcation is going to happen? How do we know what is a critical parameter such that a growth will go back to extinction? A sustainable model will become a not sustainable solution. So it has very, very practical meanings. For example, how everybody fish, right? But how much should you fish? You always have those kind of laws to say, hey, if the fish is below a certain kind of threshold, is shorter than that, put them back into the population. Otherwise you will let bifurcation occur. You will actually make the whole race go to extinction. Okay, so that's our goal. So of course, we want to do it mathematically. But keep in mind, you are trying to avoid this extinction of populations because you don't want bifurcation happen so that your solution changes dramatically or fundamentally. Okay, so definition, bifurcation. Okay, the definition is given by a small change in parameter will lead to a dramatic change in the long-term behavior. And when I say long-term behavior, like we said, we need to consider two things. Number of equilibriums and the type of equilibriums, going from a sink to a source to a node. Okay. Now let's see how this will happen. Let's see example. We have y prime equals y squared minus 2y plus mu. Okay. We define it to be f mu y. Before we have fy, now our f actually depends on this parameter mu. So this is called the parameter which can change. Okay, like the harvest rate or things like that. Now for different mu, you are going to have a different ODE. For each ODE, you can have a phase line. Therefore, we can actually draw a lot of phase line. Not just one, but many, for different values of mu. Okay, so let's draw some examples. If mu equals 0, what we have is y prime equals y squared minus 2y. Okay, we can draw the phase line. Let's do it in a different way. Mu equals 0. Okay, y prime equals y squared minus 2y. Okay, you have 0, you have 2. Okay, so that's what we got. And then let's see. What do I want to do? I want to have 0 and a 2. And what I have is this. You can do it by yourself. Okay. Mu equals -3. What you have is y squared equals y squared minus 2y minus 3. All right. So what do you have? You have a 3. You have a -1. Going up, down, up. Similar thing. Actually, we should put them in ascend order, so it's easier to see. Now keep increasing. Okay, we can increase in mu equals 1. What's gonna happen? What's gonna happen is you are having y prime equals y squared minus 2y plus a 1. From here you can see you only have one equilibriums, which is 1. Okay, up, because it's both positive. The reason is because this is y plus 1 squared. And finally, you can have mu equals 3 or 4 or 2. Okay, you have y prime equals y squared minus 2y plus 2. If you solve this one equal to 0, you will find there's no equilibriums. So the whole thing is clean. And you only have one type that is going up all the time. From here, you can see the phase line will actually tells you where the equilibriums are and what type of equilibriums you have. You have a source. You have a source. You have a sink here at the -1. Now you increase your mu. What happened? You still have a source. You still have a sink. It's just at different location. It changed from -1, 3 to 0, 2. We will call this one a small change because you didn't change the number of equilibriums. You still have 2. And each equilibrium still have the same property. It's a sink, it's a source at the same location, at a different location. However, you can see at here, of course, your solution fundamentally changed because your number of equilibriums went from 2 to 0. So bifurcation certainly happened in between mu equal to 0 and mu equal to 2. And if you really think about it, it happens exactly here. Which means before that, you will have 2. After that, you will have you have 0 equilibriums. So this is exactly where the bifurcation happened. So that's the number we are looking for. And if this one has any meanings, for example, if this one is corresponding to the harvest of fish in real life, you probably want to say, well, this is the critical point. Before that, you will have some stable solution or something like that. But after that, you may face a mass extinction. Okay, so that's the idea of bifurcation. Our job is try to actually draw this or find where it is. From here, you can see it's very easy to do. If you can just draw multiple, and then to figure out where the bifurcation happened. Okay, you can have mu equals whatever, and we know it happens at 1. Maybe this is 0. Maybe it's -1, -2, -3, -4, and this is 1, 2, 3. All you need to do is just starting draw several points for each cases, and it's not hard to see. And eventually it's here. Okay, and nothing from there, starting from there. And then you can do for each one. So it's always a source, and starting from here, everybody become fundamentally increasing. And finally, you can actually try to connect all the points to try to see the gradual change. Okay, it's not exact on the points, but I think you know what I mean. So this connection of a lot of phase lines with the corresponding equilibrium points, as well as the arrows that tell you sink and the source, okay, will actually give you where the bifurcation happened, which is happening at 1. All right. So next time, if you want to find the bifurcations, a nice way to do it is probably just draw several cases for different mu, align them all together from one side to the other, make sure mu is increasing or decreasing so you know how the thing gradually change, and then just take a look at it and try to figure out, okay, Since this one is going down, the one on the top is going down, the one on the bottom is going up, and then eventually they merge together. So everything in between will disappear. The thing above will stay, the thing below will stay, and eventually the number of equilibrium changes. Okay, and you can see as mu become bigger, the two equilibriums you originally have become closer and closer and closer to each other until they actually hit each other. That's when you have only one, and after that, they're not there anymore. So that's one way of doing it, by drawing a lot of phase lines. That's step one. And you can use a computer to aid your process. But basically, you just do examples until you see the trend. All right. Do we have a better way of doing this? Well, that go back to this. The blue line here, which I draw by drawing a lot of examples, looks like a parabola. Do you have a feeling or like a guess where the parabola come from? Knowing that this is the parameters, the ODE with parameters that we're trying to solve. Clearly the parabola come from here. Right? So how many equilibriums do you have? It really depends on how many solutions do you have for this one. How many equilibriums? Totally corresponding to how many solutions the quadratic equation has. And do you know how to do that? Of course, quadratic formula, right? We have b squared minus 4ac. Okay, that is negative 2 squared minus 4 times mu. Okay, and we have several cases. Okay. Okay, if this is bigger than 0, 2 solution, therefore 2 equilibriums. If this one equals 0, you exactly have 1 solution. That's when you have a perfect square. Okay, and when this one is less than 0, we have no real solution. You may have something complex, but there's no way you can put it on a phase line. Therefore, there's no real solution. Okay, so where does bifurcation happen? It happens exactly here. You went from 2 to 1, and therefore 1 to 0. Okay, where is it? That's where mu equal 1. So that's another way to figure out where the bifurcation happened. Okay, when mu is less than 1, you can try to find it. You will have this case. And when mu is bigger than 1, you will have this case. It's very easy to figure out. So therefore, if you have quadratic, or let's say this, if you're trying to find out what kind of equilibriums and how many do you have, you are going to solve this differential equation with the mu there, right? So what you have really depends on how many solutions do you have. Therefore, you can transfer the whole finding number of equilibrium problem to finding the solution of an algebraic equation problem with different mu. And then when does bifurcation occur is when the number of solutions of the algebraic equation is changing. For this case, it's quadratic, and we know so well about quadratic, so we know. We use our knowledge about solving equations to find this. All right, that's the second way of doing it. The third way, we want to go with the parabola a little bit. Another way to think about it is this. You have y squared plus minus 2y plus mu equals 0. Not 0, just this one. Okay. So if you think about it, okay, for different value of mu, you are going to have different value of y. Okay. So if you pick your y to be this, what's going to happen is you are going to have some parabola opening up like this. Okay. Now what will this mu do? Well, as mu become bigger, you can see basically what you're trying to do is you're trying to shift this parabola up Let me write it down. This implies shift the parabola up. Okay, and what do you wonder? You wonder how many solutions are you going to have. From here you can see for small mu, 2 solution, 2 dots intersecting with where fy equals 0. I forgot to put here f mu y. Okay, for big mu, which means you shifted the whole parabola to here, then no solution. So somewhere in between, the thing changed, and you can see by graph, you know where the whole thing changed. That's here. When this one is tangent to this one, bifurcation happens when the parabola is tangent to the y-axis. Okay, be careful here. The y-axis is actually the horizontal axis because we put y here. Okay, don't say like y-axis is actually the vertical. So from here you can see it's another way to find where the bifurcation happened, and also to interpret how many equilibriums you are going to have. It's basically starting from 2 for a small mu, you move up. If you move too much, you have no more because your parabola does not intersect with the y-axis anymore. And then somewhere in between, you have exactly 1. That's when your parabola barely touch it. Then the problem reduced to how to find the mu such that the parabola barely touches the y-axis. That's when you have a perfect square, right? It's always positive and only 0 for 1 point. Or you can think about that's when you have some vertices where the y-coordinate of your vertex is actually vertex is actually 0 to solve it. All right, so that's one way. That's 3 different ways to think about this. I would say for some nice functions, go with the second and third. The first one, you need to draw a lot of points, which we do prefer not to do. All right, that's what we need. Now let's just try several more examples. Because the ideas are the same, we just need to get it familiar with how to do this. Okay, the first one, let's put it to be a whole separate thing. Examples. Okay, the first one, we have y prime equals y cube minus ay. Okay, so find where the bifurcation occurs. Okay, now let's solve it. Again, you can draw a lot of phase lines to see what's going on. It's gonna be difficult. Okay. So what we can do is we just wonder, this one has many solutions. So when will this one has the number of solutions change? Well, we are solving this. Okay. Now what we have is we have y equals 0. And this one to solve more precisely. This one will always work, regardless of A. So you always have at least one equilibrium. Okay? Y squared equals A. You know where the bifurcation happened then. Let me say. 2 solution. If A is positive, no solution. If A is negative, that means you have y squared equals a negative number, which is no real solution. Okay? And then you know in between one solution. Where the positive and negative become the same, we have this. So when does bifurcation occur? Here. So we finally have the number of equilibriums. When a is bigger than 0, we have 3. That's 2 from here and 1 from here. Okay. When a equals 0, we have 2. That's 1 from here and 1 from the y equals 0. And a less than 0, we only have 1. Okay, so bifurcation occurs at here. Occurs. At a equals 0. And before and after, you can actually tell people how the things are going to change. All right. Now let's try a different way of solving this. Remember, we can do it by graph. Okay. So what's going to happen is you can take out a graphing tool, such as Desmos. Okay, and then you type in the graphs you want, which is, for simplicity, let's type it to be x. Okay, for Desmos, x cubed minus a times x. And we add a slider of a, which means as a changes, your function will change. Now you see what's going to happen. For small a, this is for small a, and for big A. Okay, so before you have only one equilibriums. And this one start to rotate. And then you have 3. So what happened? When did that thing happen? It happens at here. When you have exactly 2. Okay, actually, if you think about it, you actually only have 1. The reason is because you do have 2, but this one also gives you y equals 0 at here. So we need to erase this. We have 2 of them, but they actually overlap with each other. So that thing changed from 3 to 1 dramatically. All right, so judging by the graph, you can tell. It went from, let's see, from things like that. A is less than 0, okay, and gradually become things like this. A equals 0, and finally a bigger than 0. So the whole thing is almost like rotating clockwise, meanwhile bending as a become bigger and bigger. Okay, so where does bifurcation happen? It happens here. From here, you can see, judging by the graph, it's difficult to get an accurate answer. Probably you want to still, even though you get the graph to get a feeling of what's going on, you still want to go into those kind of algebraic computations. Finally, of course, if you really want, you can do this, phase lines. I'm not going to do it with detail. You can try it by yourself. But basically, the phase line you are going to get is something like, oh, actually, I didn't do this one, did I? This should be the case. Not this one, so take it back. Phase lines, you can draw it by yourself. I only did the first 2. Okay. Usually we don't use it unless we're desperate, but I would say it doesn't hurt to try it and to try to get what's going on here. All right, first example. Let's do one more. Okay. All right. Now, what do we have here? Let's take a look. All right. So, I think I will just draw the phase line. I think it's not hard for you to see. The graph looks like this. Okay. Correspondingly, if you want to do things in graphs, you can see I will actually draw it. It's gonna be x times (1 minus x squared) plus a okay. So you can see you have a graph like that. Okay, and when you change the value of a, this graph basically move up and move down. Let's make it more dramatic here. Okay, you basically just change the location of this one by moving it up and down. Okay, so there's nothing surprising that the whole phase line looks like this. So clearly, we went from one equilibrium, okay, go all the way up to here, when you have 2, right here, and then you have 3. So 1, 2 equilibriums here, 3 equilibriums in between, 2 again, and then 1 again. Okay, where does it happen? You can actually shift this thing up and down to figure out where it happens. Let's set it to be 0. Here. Okay, so set. Hold on. Let me make this one clear. For graph, this is what you should do. Okay, I want to draw the shape. Okay, I want to select it here. Let's see, make a copy, paste. The first copy goes here. So at first you only have 1 equilibriums. After that, what you do is you shift the whole thing up to be just right. Let me change it to be blue. Then you have 3 equilibriums. Okay. Finally, you have this one. Let's make it green. You shift all the way up, then you have only 1 equilibriums again. Okay. So, of course, we have this kind of process. Great. But how do you find where the point is? Like, how do you know this point? Oh, that's supposed to be green. Okay. How do you know where the point is? Like when you have only 2. If you think about it, the first case you can do is you wonder y prime equals y times 1 minus y squared plus mu. Okay. Has only 2 solutions. That's where the bifurcation occur. It did for twice. No doubt. Okay. But the problem is, how do you find where this one is? For which y value? For which mu? Will this one only have 2 solutions? That's something that you do not know how to do. You only know there are 2 cases, right? One happens here, and one happens here. But you don't know how to do that. Therefore, you need to ask yourself, how can I find these points? When I shift it up and down, how do I know that I'm just right at that I only have 2? And I think it's not hard to realize. It has to be one of these cases. It's either this, okay, or this. That means it's either when this one is tangent to the y-axis at here, or it's either it is tangent at there, at here. Okay. So even though solving this one directly, you cannot do it, but what you can do is you can solve the second derivative. Solve the first derivative. So you take this one. Okay. Let me make sure. What we have is y over 1 minus y squared plus mu equals 0, but we can't solve it. Can't solve for mu. Because don't know why. Okay, we have y and mu to be unknown. But additionally, we know one more thing. That is, when the bifurcation occurs, y, the graph is tangent to the y-axis, which means f prime y equals 0 at this y and here. So then these two y's, not only f prime y equals 0, fy also equal to 0 because it is on the axis. Therefore, they should satisfy this. So we have a system of equation involving y and mu, and this time it should be doable. Before we only have one equation, but we have two unknowns. Okay, so let me just write it down. Meanwhile, you know f prime y equal to 0. F prime y, okay, that is f prime y is going to be 1 minus y squared plus y times 2 1 minus y times -1. Okay, or plus 0 because mu has nothing to do with y. Therefore, we have number 1 and 2. Let's use A and B. Okay. Then solve for B. We know y minus 1 plus 2y equals 0. This gives you y equals 1 or y equals 1/3. Now we will be corresponding to this point and this point. 1/3. 1. Okay. Meanwhile, that's where the bifurcation happened. So you just need to figure out the corresponding mu. So plug in into A for one case. Because you have 0 plus mu equals 0. And for y equals 1/3, you have this one implies mu equals negative. So the bifurcation happens twice. At mu equals this, and mu equals 0. If you really want to differentiate it, you will see you can differentiate the whole thing, which is mu, into several parts. Before you have one equilibrium. In between you have 3. You have 1 after that. And you have 2 exactly at here and here. Okay. Corresponding to the graph we have, which is but now we know exactly where these 2 points are. That's where the bifurcation happened. All right. From here, you can see there is no uniform way that I can tell you how to do bifurcations, because the function here can vary. It can be sine, cosine. It can be exponential, or any kind of algebraic equations you can have. Sometimes you just have to do all the algebras and function transformations, for example, in this case, and maybe sometimes taking the derivative as we are doing here in order to find where the bifurcation occurs. All right. That's roughly the idea. We went over 2 examples. Finally, probably we can go over with the fish harvesting example. So number 3, applications. Okay, so what we have is a logistic growth of fish with harvesting. Okay, now we have DP. I will use the one consistent with the book, because for us we use the Y, but they use P, standing for population. So the parameter here is C, the amount of harvest. Okay, the example we give at the beginning was harvesting with C times a Y. So we harvest a fixed percentage. So for example, the one we had was HY. So what we can do is we can divide the lake into several blocks, and then we just fish one of the blocks. So assuming the fish are equally distributed. Okay, so if you have more population, you are going to fish more. If you have fewer population, you are going to fish fewer. That's one way of doing it. We saw what happened. Now what they are trying to do is they are just going to keep fishing for a fixed amount. That means every day you just fish for 5,000 fish. If you have a bigger population, you fish for 5,000 fish. If you have a small population, you still fish for 5,000 fish. From there, you can see, okay, this can really do harm to the environment, because if you have only a few populations already and you keep fishing a fixed amount, it's very possible you're going to kill them all. Okay, so now let's see where the bifurcation occur. All right, and now we know. We're just trying to solve this one and try to see when does this one equal to 0. This looks fancy, but really, if you just factor everything out, this is nothing but a quadratic. Okay, if it is a quadratic, what we can do is we can simply just do the determinant. Okay, that is b squared minus 4ac. And we know the bifurcation happens here. Yes, let's do that first. Plus or minus plus 4 times k times c equals 0. Yes. Okay, 4 times k times c equal to 0. That means your k does k, or let's see, your c is going to equal, what is it? Negative k squared over n squared divided by 4k, which is negative 4 n squared k. Then the whole thing become what? Okay, let's see this. Number 1, we have this. Okay, you can try to see if c is a little bit bigger than that. P. Yep. Okay. So let's draw this. This is going to be a parabola. Okay. C basically shifts the whole thing down. So the bigger the C, the more likely this one is in below. Therefore, what we have is some graph like this. When C is less than that, small equilibriums. When the C is bigger than that, we stop. Okay? No equilibriums anymore. And if you draw the phase lines, you are going to have let's use blue to just do this. Exactly the opposite. Remember, the one on the top is going to be a source, the sink, and the one on the bottom is going to be a source. Okay, so after that, what do you have here? Basically, you just have something that's going down all the time. If you draw it, take this one out. Or let's just do this. Okay, for small c, you have this. Therefore, your population will still go like that. Still go like that. You just have a lower and lower equilibrium. But once you have a big C, you will have something like this. That means your population just keeps going like that. You go to mass extinction. Okay, you kill all the fishes in that thing. So what will happen? Where does that thing happen? It happens right here. That is where the bifurcation happens. So that will be the critical fission rate that you want to avoid. Okay, you need to do smaller than that. All right. That's all we got from quadratic. And you can even plug this one back in to find the solutions. The solution is going to be P equals plus minus okay, and go ahead and try to do it by yourself. You can see this one has 2 if n squared over 4 minus cn, okay, is less than bigger than 0, which means c is less than 1 and 0. Solution corresponding to this one equals 0, and this one is less than 0. Therefore, this corresponding to c equals nk over 4. This one equals c less than nk over 4. This one goes to c bigger than nk over 4. For here, you're fishing too much. You destroy the whole thing. Okay, but above that, you're okay. It's still sustainable. Okay, somehow my computation didn't match what I have here. That must mean I had some mistake here. Kp minus. The reason is fairly easy. This is your B, and this is your A. I did exactly the reverse because I wrote P first. So I better just complete the computation here. Ignore what I did before. The idea still works though. I just got a different number. Okay, so negative k over n p squared plus kp minus c equals 0. Therefore, p equals negative plus or minus b squared minus 4 times kc over n. All right, and then go ahead and try to solve it. You will have whatever I have here. Paste. So the bifurcation occurs at nk over 4. Okay, so that's where the bifurcation happened. C equals nk over 4. Before that, 2. After that, none. So this one is right where you have only one equilibrium, okay, which is still still a node. Everything goes now. All right. From here, you can already see it's working. K divided by K has n there, and then you probably times K square somewhere to divide the whole K square out. Then this one is gone. You times n back there. This one looks legit. All right. Can we do that? Fairly easy. Now we just harvest. But this time we don't harvest by h times y. We just harvest by h. You can easily see, okay, for small h, probably I need a bigger h here now. Let h go from to 30, maybe? Probably not 30. Let's do 1,000. I started with 1,000 fish, so probably let's do 1,000. Okay, at first it's nice. You fish 100. You see that thing kills the whole thing up to 1,500, but you still have 2 equilibriums, so you still have a final sustainable population at 1,500. You do another 200. You can see it already breaks, so probably let's change it to be between 100 was okay, so 150, maybe 200. Hold on, let's do 10. All right. Now what we have is actually if you fish for nothing, you still have the 2,000 capacity. Okay, now you fish for 40. It reduced the final population, but still sustainable. You fish for 100. Still all right. We are at 1,500. Now let's do 130. Okay, 150. Okay, 170. And suddenly the whole thing breaks, because that's when you stop actually having the equilibriums. So it's right between 150 and 170. Okay, probably 150 is right where you only have one equilibrium. From here you can see. Now remember, it's nk times 4. The k I picked here is, where is it? A k is 0.3. Your n is 2,000. Yeah, so nk over 4, if you think about it. Let me put the parameters of my code there. N is 2,000. My k in the code is 0.3. nk over 4 is 2,000 times 0.3, which is 600 divided by 4. That's exactly 150. So the bifurcation occurs at 150. And from here you can see at 150 you have exactly one equilibrium, which is you don't change at all. Before that, nice logistic growth. After that, a disaster. All right, that's all for bifurcations.